Okay. Hello and welcome back, everybody. So now I had the opportunity myself to try the famous Alma burger as well. So my students have been talking about it for quite some time already, but now I understand it. It's not actually famous. It just contains those letters in its names, and my neural network tends to associate the semantic meaning to the word. But other than that, you know, that's the end of the story, apparently. Okay. So I'm very happy that we have Yingqian to give the second presentation of the day. So while Quentin in the morning was talking about this longer-term ambition for a generic RL-based solver that can solve any combinatorial optimization problem, Yingqian will tell us about her experience using deep reinforcement learning for practical OR, operations resource applications, including many. So Yingqian is at TU Eindhoven. She has been working at the intersection of machine learning constraint solving for a long time as well. So she's, for example, one of the executive board members of the DSO Euro group. That's a Euro working group, so from within the operations research community, on data science meets optimization. She's been organizing a ton of workshops on that topic, also special issues. She was also involved in the competition that Wouter Kool talked about on Wednesday. And so, yeah, lots of interesting work going on. So I'm very happy to hear about your work on deep RL for industrial OR problems. Let's give her a warm welcome.
Thanks a lot, Tias, for introduction, and thanks for inviting me. So I'm not a CP researcher, so I'm not going to talk about the CP techniques today because you know probably more about it than me. So today I'm going to talk about real optimization problems. I'm going to talk about deep reinforcement learning, how they can be applied successfully in solving those type of problems. So I work in industrial engineering department. I have been working on solving optimization problems for a very long time, or not so long, but quite some times. And when AlphaGo came, beat the professional Go player, I was, wow. I started to look at also how deep reinforcement learning can be used in solving difficult optimization problems. So I start with Dutch Railway. Together with them, I look at how we can park trains during evening, so in the shunting yard. So this is optimization problem. So back then, that's 2017, we had a solution already which is better than local search. So it gave me a lot of confidence in having deep reinforcement learning as a main force to solve difficult industrial optimization problems. So of course, also along the journey, I have lots of not so successful stories, but today I promise that I will tell successful stories to get your interest in deep reinforcement learning. So here we go. I will give a very short introduction of DRL. I believe everybody here knows a little bit about DRL already. And then 2 successful stories. Okay, so very briefly, RL is inspired by how we learn, right? So we have an agent, we have an environment, and the agent observes the environment and do some actions, and the environment gives some rewards. Sometimes the reward is delayed, right? It's how it differs from the supervised learning. And basically, it is trial and error search, right? It is it's learned by interaction. So this is the famous diagram. So there, at each step, what the agent will do, agent will pick an action. So agent will yeah. Oh, okay. So agent will pick an action and observe the new environment and also receive some type of intermediate reward, right? From the environment side, it receives action from agent and it do something with the action and it outputs a new state and also maybe give some reward to the agent. So this everybody should know. Basically, it gives a very nice framework for learning to solve a sequential decision-making problem, right? You learn to update your policy to output better and better action through the interaction with your environment. All right. Okay, so of course, we understand in many, many problems, the number of states, action space are very big. So that's where the deep learning comes into play, because everybody knows deep learning has the magic power to approximate these large states. So this comes deep reinforcement learning. If an agent is going to use these deep neural network architectural models to predict which actions to output next state. All right, so this is some algorithms in the modern RL. So basically, RL algorithm has two classes, right? One is model-free and model-based. So the famous AlphaGo goes with model-based RL because it has a model. So they also know the rules of the game. So it builds a model, and they use the planning algorithm to roll out to estimate the how good the action is. So it has a model. And now a lot of algorithms developed for the model-free RL. There you have a policy optimization algorithm where the agent learns to output the action directly. And with the Q-learning type of algorithm, the output is the value of certain action in certain state. How good is this action? Yeah? So there are different type of algorithms. Okay, success stories of DRL. Why we run into DRL nowadays so often? All right, 2015, so this Atari games. So there, the researcher, what do? So agent here, they only observe, they only see the screen, right, the pixels. They only see the screen and the score, and they learn to play the game. And by doing that, using reinforcement learning algorithm, they can have the human level performance for many, many games. So back then for that, I was thinking, wow, but to me it's more like a computer vision thing still, right? I was not so touched. All right, then of course the AlphaGo comes. And 2016, AlphaGo beats the Go Master, so that was the big shock to me, right? Because basically this is a planning algorithm, so they are so good at solving this huge planning problem, and they can beat the professional player. So then we start to think also how we can also use it in solving other type of not exactly traditional planning problem, but optimization problem. They have some similarities, right? And of course, recently, last year, ChatGPT. So in ChatGPT, they have a lot of things going on, of course, but the last step, they use a model-free algorithm, PPO, to optimize the policy, to optimize the output to the user, to make the dialogue better. Yeah, so this is really another very successful use of deep reinforcement learning algorithms. Now, of course, together with many researchers, it's our dream to put solving combinatorial optimization problems in one of the successful stories of DRL, right? So that is what we are trying to do and trying to achieve all these years. Okay, so coming back to this optimization problems. So in the real world, we have lots of optimization problems. Most of them are just different variants of classical combinatorial optimization problems, right? So if you look at package delivery, you need to plan the route, so it's a variant of unique routing problem. If you look at the harbor or in the train station, how they stack a package, stack containers is a bin packing problem, right? So when we do this train shunting problem, it's also 2D bin packing problem. So we have checks, train comes in, we decide where to park train, right? We just have a little bit more constraints because train also need to get out of the track. So you also have a timetable constraint. But it's variant of the bin packing problem. And of course, a lot of in the manufacturing systems, you have a lot of machine scheduling problems. So there are the real-world problems I'm looking at in my group. Okay, so today I'm going to discuss two types of optimization problems which have successful stories. The first one is a stochastic sequential decision-making problem. So basically, in this type of problem, you really need to make a decision quickly in real time. For example, in ambulance dispatching. So when you get the call to get ambulance, you have to decide which one to dispatch. Yeah, so you don't have time to run the solver to solve the problem. And in the warehouse, so I work with bot.com. So there's a huge e-commerce company, right? They have a big warehouse. There, they receive thousands of orders every hour. When they receive an order, they need to decide how to batch the order, how to pick it up from the warehouse, such that all these orders can be shipped to the customer before the deadline. So in this type of problem, you don't have time to collect full information and optimize decisions. So it's a really very difficult stochastic sequential decision problem. And also, if you look at the OR community or optimization community, we really don't have good solutions, right, for this type of problem. So typically, okay, you can do the stochastic programming, but you know the limitation, right? So yeah, you cannot handle large problem size, and you have to think of different types of scenarios, and you can never cover all possible scenarios. So in practice, for this type of problem, what do? They typically come up with heuristic rules. For example, ambulance dispatcher, they see, I'm just going to pick the closest ambulance to the location. I'm going to dispatch that. So it's a very typical practical rules they come up for this type of problem. Okay, so I have a lot of successful story about solving this problem using machine learning. The second class of problem, so there we have a little bit more information. Yeah, so for example, we know what jobs need to be scheduled on the machines for tomorrow. We know that. But sometimes, of course, during execution, some uncertainty can occur, right? There are some stochastics. So for this type of problem, it's a little bit tricky to have an end-to-end machine learning solution, but I will tell you how we make it successful for some of these problems. All right, are you ready for the successful story 4.1? So this work we did together with Founder Lambda. So this is the company who provides a solution to warehouse operations, airport luggage handling, and packaging. So of course, I have students behind, brilliant students behind to do this work together, Igor and Luca. So here what we look, we want to solve these collaborative picking problems in the warehouse using end-to-end reinforcement learning. Okay, a little bit of background about the problem. So order picking. You imagine you have a big warehouse, yeah? And you get order from, for example, supermarket. And you know this order. Once you know this order, you need to decide what order you should put together to be picked up. So it's called order batching. And when you should release this order, meaning when you should ask people to pick it up, right? It's order releasing. And then for human pickers in the warehouse, you decide the route for them to walk through the aisles in order to pick all these orders together. So they have actually several optimization problems in the warehouse. So traditionally, they use a human-only order picking. Yeah, so only human do all the work. It's very not efficient because they only spend 30% of the time picking. Other time, they are just walking around and do something else. It's very inefficient. Okay, so from this one-to-one human-only picking solution, now the industry moving towards this many-to-many swarm collaborative picking, which means in the warehouse, we have many AMRs, vehicles, we have many human pickers, So they need to work together to pick order and deliver order to the packaging desk. Yeah, so this is called collaborative order picking. So this gives you some idea how it works. So this is the layout of a warehouse. And you see the vehicle. We have many of them. You see the human pickers. So what currently they are doing is the vehicle, the AMRs, they have pick runs, which means they know which orders, in which location they need to go to pick all of these orders. And then the human pickers, they go to one AMR, they help to get the item from the shelf and put on top of AMR, then AMR can move to other desk. Yeah? And when this human picker is free, then she or he will go to the next AMR, waiting help from the human picker. So this is called collaborative picking. And of course, it is chaos in the warehouse because there are a lot of uncertainties. Like human can make a mistake, for example, can drop a box of milk. And then the truck, who is supposed to pick up all these orders, is late, right? And also sometimes they have the orders are not on the shelf that they are supposed to be. So there's a lot of uncertainties and randomness. So they want to do this matching of a human picker to MIR dynamically online. Yeah, so this is an online decision-making problem. All right, the challenge is, okay, how to match, allocate pickers to AMRs. So the requirements of the solution, I already said, is online allocation, online decision. And it should be able to handle uncertainties and conjunctions, right, in the warehouse. And the solution should also robust against the different business in the environment. And also, it needs to be robust to different warehouse sizes. Yeah, so it can be applied to different sizes of different sized warehouses. You already know we're going to use deep reinforcement learning to solve this, right? So we use deep reinforcement learning to develop a picker optimizer in this, for this problem. So the problem definition, I don't put everything there, but the objective is the total picking time is maximized, or you can see the pick rate is maximized. And the decisions are allocating human pickers to AMRs. So if you look at what we know for this type of problem, we know roughly, for example, how orders are distributed in the warehouse, right? We know the location. We know roughly how many orders are coming, what type of different orders are coming. And also in the company, they have business rules, which are supposed to be smart to assign these human pickers to different AMRs. So we know this. So if we know this process of the warehouse, what we can do is, of course, we can build the environment. We can build a good discrete event simulator to simulate the environment of a warehouse. And then we can just use a deep reinforcement learning agent to interact with this simulator in order to learn a good policy to match human pickers to AMRs. So that's exactly we did. So I'm going to tell you a little bit more about the details. So first step to build a simulation model. So we need to simulate. We simulate the orders in the system. We have AMRs, different AMRs in the system, different human pickers, and we simulate their movement. Yeah, so this is a simulator we built. And there we also inject uncertainties. For example, uncertainty of the picking time of human pickers, the speed of different speed of AMRs and different speed of human walking. We also simulated disruptions in the environment and the congestion situation. And so if you have AMR, because L is not so wide, you can't really have two AMR, they pass to each other. You need to slow down. So all this we simulated in the simulation. And then what we want to do, because we want to optimize for picker, right? So we look at this process from picker's point of view. So basically, when a picker finishes a pick, then she will send a new destination request to the picker optimizer. And this picker optimizer will tell her, OK, this is the next destination, next location you need to go. So she received this, she went there, and the pick item, again, she's available, she sent another request. So this is how it will, how it interact with the agent. Yes, is it clear? OK, now we have an environment, a very good environment. Yeah. Next step is to formulate MDP, right? In order to use reinforcement learning, we need this MDP formulation. So for optimization problem, it's rather easy, right? For the action space, of course, actions should be decisions, right? Then the action space consists of the locations, different locations. And then you can pick what is the best location next, right? So action space is just decision variables. And no, it's essential. It's essential. We only train one agent.
Okay, yeah. It's one agent, we need to make one location decision. The next step is the next agent.
So here, so agent, I avoid saying that human picker is agent. They are human picker. So agent is just the reinforcement learning agent. We only have one such agent who control all human pickers. Yeah. So once a human picker becomes available, you give him a new location. Yeah. And the reward function is also very simple usually, right? Because it should align with your objective value. In this case, is minimize the picking time. So that's why reward function is also picking time. And the most tricky part for this type of problem using reinforcement learning is state space and embedding. So eventually, what you want to do is the agent should know relevant information in the environment to help him to make a good, predict good action, right? So what are relevant information and how you embed this information such that you can learn such information, good patterns from this information is the most tricky part in this type of application. Okay, so for this warehouse, you can imagine it's very difficult to use a classical feed-forward neural network, right? Because first, it's difficult to get spatial information. It's very difficult to encode the spatial information. But in the warehouse, we do have such information. And also, the classical neural network, it's difficult to adapt to different sizes of problem, right? If you change the number of locations, it's also very difficult to adapt it in the feed-forward neural network. Yes?
Why is it hard to handle spatial information and warehouse very structured?
OK, I will get to next slide or the one next one. You will know the answer, yeah? And so that's why we look at the problem instances that agent will get as a graph. Yeah, so basically, indeed, it's structured. It has aisles. And for each picking location, we say it's a node, right? If two nodes are connected, meaning they are reachable between these two picking locations. So we represent these instances as such a graph. Yes? So your question is why these locations are nodes? Oh.
So why do we don't have edges between nodes and two houses that are adjacent?
So why you don't have? I'm too short. So here, yeah, because it's a warehouse. It's a shelf. Well, it's a shelf there. You cannot cross. No, then you will really bring a disaster in the warehouse. Yeah.
Sorry, so is the action space then just each node in the warehouse is like a location?
Yes, that's the most straightforward one, but of course you want to do a little bit smarter, yeah. No. Okay, so then, of course, there are a lot of information about the current environment scenario, right? Those we put as features in the node of the graph. So for example, for each location, we see whether there's a picker free, yes or no, whether AMR is coming to this node, yes or no, and what is the situation of the location of this node. So we put all this environmental or scenario information, context information in the node. And indeed, the action space will be a set of locations that a human picker can go. But of course, you want to make it smaller, meaning that if there are already AMR in that location, or AMR will go that are not going to that location, you're not going to include in the action space, right? And the reward function, again, align with your objective function, which is penalty on time that pass. So I'm looking at the now and the previous step, what is the time difference. Okay, so this will go to the, will answer Alice's question. Now, so now we need to look at the architecture of the neural network, right? So we said, okay, instance are represented as a graph. Then we need an architecture that can handle graph space and spatial information. And one natural thing is, of course, graph neural network, right? Because it doesn't matter what type of topology, right? You can use different size of warehouse, different number of nodes, etc. And it's also permutation invariant, which means if you change the orders of the nodes, the outcome will be the same. It's all we need. But regular graph neural network, it does aggregate information of different nodes through message parsing. It can be very heavy. And indeed, we have a good structure in the warehouse. Yeah, so that is what we are doing. We are not going to use graph neural network. We are going to use a particular structure. We call it L embedding. So for each L, we give some information of what is the information, what is the nodes information in that L. And then we use adopt invariant feed-forward neural network and combine this information together. So in this way, we don't use graph neural network, but we can handle different sizes of inputs. And we can also make sure that this nice property of graph neural network stay. Yeah? And by the way, this invariant feed-forward neural network is already also developed by Alice and his students. So I'm not going to discuss the architecture unless you have a question later on. But in this way, we use a simple architecture, yeah, and then we can still encode nice spatial information of particular layout of the warehouse. And we can handle different sizes of warehouse as input. That's very important. All right, so now we have a simulation model. We have interface between simulation and the agent, which are MDP formulation, right? States, action, and reward. And now it comes to the algorithm. So we use a PPO. So it's a policy-based algorithm, meaning the policy network will directly output the actions. And there we use act-critic architecture. We have a two network. Act network will strat actions. Now, so we'll directly strat which action to take. And the critic will estimate how good the select action is. Yeah, so it's a very standard algorithm, and it just work. As you will see in the experiments. All right, so we have built all of this, and now we want to see how good it is, right? The performance measurement, I already said, is to minimize the total picking time. And we want also the policy will be able to handle different business in the warehouse, like different scenario of business in the warehouse, and can be applied to different sizes of a warehouse. So we develop different environmental settings. So with the XS very small warehouse, there we have 7L, we have 7 AMRs, we have 4 pickers. And so in total, we have only 98 picking locations. And for the XL size of the warehouse, which, by the way, is similar to the warehouse for Abraham. So it's very big, actually. I don't know whether you know Abraham, but it's a supermarket. So for this big warehouse, you can see that we have 60 pickers, 180 AMR running in the warehouse, and have 2,800 picking locations. It's very big. So we want the algorithm works for all of this, right? Okay, so what is the benchmark algorithm? What are benchmark algorithms? So first is the benchmark from the company. So they have a lot of expert knowledge, right? They carefully think of this heuristic rules. It is based on the how the pickers are spread over the warehouse and also the distance of potential picks. So they have smart rules for that. So this is one of the benchmark algorithm. The second one is greedy. Of course, you know that in many situations, greedy just work, right? So we benchmark also against the greedy algorithm. And the third one is mixed integer programming. I know I can also use CP, right? I should use CP maybe. But okay, so this one is used to see how the policy learned from PPO, from the DRL, the performance, whether it's close to optimal or not. So we only apply to the super small scenario, XS scenario, and we remove every randomness. So it is a deterministic environment, full information, very small, then we can run the optimization solver to find the optimal solution. So we also benchmark against this. Okay, so it's a bit difficult without the pointer, but let me see. So first, we compare with the optimal solution, assuming there's no randomness, right? If you look at these two tables, we use the Groovy optimization solver to solve this LP formulation, and the Groovy run, we let it run for 20 hours for each instance, and it still couldn't find the optimal solution. I still see the gap, the MLP gap. So it's still not optimal. But you can see that the DRL solution is very close to MLP solution. And of course, DRL, we train it for less than 1 hour. And when we use to solve the problem, it takes milliseconds. Yeah? And you can see for two different scenarios. For the second scenarios, DRL are much better, or not much better, are better than the solution from the optimization solver. So it's a very good result to confirm that really the agent really learned a very good heuristic. Yeah? Okay, then we can move to the large warehouse. So we look at the performance of the DRL agent, how it compares with the greedy and the benchmark from the company. So for all these different sizes of warehouse, you can see the DRL can reduce the picking time reduce a lot compared to the greedy and the benchmark. And these results show that, so we trained the DRL agent with a specific number of picker, number of AMR ratio, resource ratio, 10 and 25, and for the small size of warehouse. And we train the policy directly used for different scenarios in the warehouse, how busy, how many pickers are there, how many AMR are there. We use directly, and you can see that the performance is just good. Yeah, it's very good performance. And it also applied to the super big warehouse. We train with the specific cases, and we apply to different type of scenarios. Basically, it transfer the performance is transfer very well in this case for the learning agent. Okay, this is the interesting part because what we want to do is we want to see, do we need to train on 2,500 picking location case? We don't want to, right? Because it took us 2 days to train that model. It's huge instances. So we see, okay, if we train on small size warehouse instances, whether the trained policy can be directly used to solve the large problem instances. And it can. So if you look at this result, for example, if you look at the policy S column, you see that is the policy trained with the S scenario. It can solve the size M better than all other, if you even train on the size M scenario, right? It transfers the performance very well. And if you look at the policy L, it gets a better result. If you train policy L, I think we train it for 4 hours. We apply the policy directly on the huge size warehouse, and we get the value 8,567, which is better than if you train directly on the huge warehouse. So, so the policy trained on the small size warehouse really transfer very well to the bigger sized warehouse. So it's very good result. All right, so we also want to look at, of course, graph neural network, right? How it works. In this case, so we use the inferent feed-forward neural network, the first column, and also 2 different graph neural networks. So we compared with the architecture we designed is the second column, and you can see that the performance is better with our encoded information of the layout of the warehouse if you compare with other architectures. Yeah, so you don't need to use a graph neural network, it means. And of course, if you look at the inference time, if you use a simple feed-forward neural network, of course, it's the fastest, right? And if you look at graph neural network, they take longer. That's why we don't want to, if we can use a simple architecture, we don't want to use a complicated one, right? All right, so yeah. I talk a lot about efficiency, right? It's, of course, company wants that. Now, at some point, I asked, don't you care what the human pickers think? You can't just give them a task. For example, if I need to always pick a heavy drinks, it's not fair, right? They said, yeah, it's not so important. But then we talked to an ergonomist, you call this that, in the company, and she said, yes, of course it's important to take care of the physical situation of the workers. So then we agreed it's also important to put workload fairness as one of the objectives of the agent. Yeah, so then we have a multi-objective deep reinforcement learning problem. So we want to optimize efficiency, but also workload distribution among different human pickers. Okay, so I will not go to detail, but again, what you do is you define what is your objective, what is your reward function. You add the one, right? You add the one is fairness. And also in your state representation, you add the attributes of fairness in your state representation. And then we use a meta policy approach to learn this multi-objective reinforcement learning. At the end, it will give you a Pareto front. So you see here is one objective, here's a value of another objective. What is the solution looks like in this graph? You will see later. So this is a result. I think you cannot read, so I have the bigger one here. So it's the result on the large size warehouse. The blue ones are learned from multi-objective deep reinforcement learning. You see they have very beautiful front, right? Because the ideal solution will be the left lower corner. There you have the lowest picking time and the best fairness. right? The best solution will be there. But the blue ones, you see, is very, very good performance. And of course, if you look at, if you only optimize for efficiency, is the orange one, or no, yellow one. You get a point over there. It has good efficiency, very low peaking time, but the workload distribution is not fair, right? It's quite a large value there. So then you see the effective of having this multi-objective learning. So this is how also we inspect the behavior of different policy, right? So we use different heuristic learned from agent, which is a DRL, and also using Grady and using the benchmark from company to give orders to human pickers. And we see the simulation, and at some point you will see this phenomenon, which is DRL is able to spread human pickers across the warehouse. And for the another two heuristic, they cannot do it. Yeah, so this is behavior difference from different policies learned, use different methods. All right, and I'm obsessed with decision tree, yes? Across all pickers, yeah. You want to have a lowest standard deviation. So similar weight, yeah. The total weight they pick, we want to keep them the same, yeah.
200 kilograms of standard deviation. Doesn't that mean that it's a lot of deviation? Like it's a lot of variance across all the.
Yes, I don't know whether I understand your question.
So, in your previous slide,
Yes.
standard deviation is around 235 kilograms.
Yeah.
So, is that normal in the industry that you have so much of standard deviation?
Well, so it runs for 100 episodes. So it's add up, yeah. But it is, so if you look at if you are always asked to pick the very heavy drinks, etc., right, then, or one person is only picking the chippies, then you can have a very different workload, yeah. Okay, so the last part. So I always think, so the deep learning model is a black box, right? I like decision tree. So let's see what the decision tree will look like if I translate the learned policy into a decision tree. So that is what we did. We approximate policy behaviors from this agent to decision tree. And very surprisingly, I didn't expect the performance will be so good. So if you look at the front to front again, so the let me see, the green one is multi-objective policy learned from DRL, yeah, and the blue one is the approximation by a decision tree. They are not so different, right? The decision tree is still very able to give very good decisions. Yeah. And of course, I also test all this transferability and to apply this decision tree to different sized warehouse. Its performance is much better than the Grady algorithm or benchmark from the company, and not too far from the deep reinforcement learning agent. Okay, so to conclude this case, we can easily increase the efficiency for this case. Yeah, so we can increase it to 40%, which means actually they can use a much lower number of human pickers and AMR in the warehouse. So it can save them a lot of resources. And the algorithm show also we have very good trade-off between efficiency and the fairness. For the large warehouse, the policy can increase the efficiency by 24%, and also over 90% of fairness. So basically, it means you really have to look at the fairness, right? Because, yeah, you can do a little bit to, the price of fairness is not high at all, actually, in this situation. So if you care about the fairness, put it in the objective, and the learned policy will not sacrifice the efficiency too much. Yeah, so this is a message. And it's definitely show that the DRL approach really works for this case. It also has very good transferability to different scenarios in the warehouse and to different size of warehouse. So to answer the question, is it ready? Is DRL ready for solving this type of online decision-making problem? My answer is yes, because it's definitely better than handcraft heuristic used in practice, right? I will not say that the heuristic we learned from DRL is optimal. Nobody knows what is optimal heuristic in the online decision-making setting, but it's much better than the handcraft heuristic. So this is really, it just works. And what is the recipe to make it work? Of course, look at the case. So of course, this only works for this specific case, right? This warehouse operation with the collaborative picking. You need to build a good simulation model where you can, okay, yeah, I'm not going to talk about that, but build a good simulation model and represent your problem instance well, so such that the agent can extract useful patterns from the information you gave to the agent. And also make sure that your architecture is size agnostic and general, so you can apply to different sizes of problem and different scenarios of the problem. Yeah? And then you can apply either model-free or model-based DRL algorithms. So we also have, over these years, we look at this type of online dynamic decision-making problem using DRL for different settings, different applications. So these are just a set of references. Still, of course, I'm a researcher, right? I'm always looking for the research challenges. There are still challenges there. So for example, we didn't pay attention to a lot of hyperparameter tuning or algorithm selection, right? Last, it will help, right? Yes. So AutoRL is something we can look at to improve the solution even better. Of course, AutoRL is a little bit more challenging than AutoML because evaluation takes a lot of time, right, for reinforcement learning. And what I said already, instant representation is so important for solving optimization problem. So what information you should give to the agent and how you encode this information. So we are also looking at how to encode information using different architecture. Yeah, I always think if we don't need to use a deep neural network, we don't, right? So Daniel sitting over there, he also already had a paper this year to look at how to use a decision tree to learn MDP. That is also something we should really look at. And of course, we built this simulation model to represent the real world, but it's not the real world, right? So this problem from the robotics community seem to still exist in our problem. So I already said we also use like a model-based algorithm. It also gave a very good solution, but we don't know actually if we apply this different type of algorithm in the real world, how it will look like, and what is the tricky part, what is the additional challenge we need to address. And whether this challenge is the same to the challenge from the robotics community, I also don't know. But this is also an interesting topic to look at. And adoption, right? Adoption is something totally out of my hand because these psychologists, they have more insight than me. How people in practice, they will adopt your solution, yeah, it's a challenge, to be big challenge. All right, so before I move to the successful story number 2, do you have questions?
Why do you use single agent reinforcement learning when you have multiple figures?
Yeah, so one answer is it's not necessary to use multi-agent because it's a collaborative setting, right? We need a centralized algorithm. And we know centralized algorithm, if you can make it work, it's better, it has better solution than distributed algorithm. And you can see we can handle the really very large sized warehouse with a single agent learning. So it's not necessary. But I can imagine if you look at taxi dispatching problem, right, in the New York City or in Shanghai, then probably you have to look at it from multi-agent point of view. Yeah, because that is a huge space. Yeah. Yeah, it's not necessarily true. Yeah, it's not necessarily true. You mean if you have some basic constraint of capability, right? It's not necessarily true. You don't have to use multi-agent. Yeah. Basically, you need to encode this capability. Yeah.
Can you repeat please what is exactly the agent controlling the location and the worker? Like what to pick and who is picking it up? Or
So the agent controls which location this human picker go next.
but there are multiple workers, so it
Yes.
control also which one.
Yes, yes. But in this very dynamic situation, typically at each 10th step is only 1 or 2 pickers become available. Yeah. But if there are multiple, like 10 pickers available, you also need to do choices, which one to match first. We have another work to look at that situation, and I didn't mention here. You need a different architecture, multi-head, for example, to handle that, to pick which one to decide first. And once you pick this human picker, then you decide the next is which location to go. Yeah.
In your graphs, there were like 6 different oral policies represented with the same color. Is that like 6 different agents or just 6 different like maybe warehouse sizes?
6 different agents. 6 different agents with different weights for different objective. Yeah.
In the real world, do you always have the exact location of the pickers?
So in the warehouse, the location is fixed. So location,
Location of the aisle and shelves of it,
yeah.
where the pickers, is that also in real time being sent to the centralized?
Yes, this is the information that agent should know. Yes.
Is that what also happens for the adoption? I'm thinking in terms of the adoption.
Thanks for thinking of that. Yeah. So now we are really looking at how to implement it in their software. We haven't thought of that, but indeed we would do that, right? Because you can get. No, we are not going to do that. Sorry. So you are talking about the real-time location of each picker, right? We don't care. We only care when picker is here to picking, and when and what's the next location he or she has to go. How he go there is the warehouse is very structured, and so the distance. Of course, you have some randomness of the time you spend on the road, but yeah, it doesn't matter too much.
But in order to match a particular picker to the location where that picker has to go, you need to know the picker's location.
We know, right? We know.
Okay, so that's also what happens in the real world.
Yes, yes, yes. Yeah, yeah, yeah.
Everyone has been given
They start with a location, and the next location will be the location you send him to, right? And then the next one will be the one you send him next, so you know.
so that's an assumption that the person is going to stay at the location.
Yes, that's very good. Yeah, good point. So there's also randomness here. Yeah, but it doesn't really matter for these dynamic online decisions. You have randomness. That's why deterministic algorithm doesn't work, right? Yeah.
So when the agent chooses to reach the packet, which path should it choose?
They have a very fixed route. You mean the routing problem, right? So it's quite, again, you cannot just move across the shelf, right? You have to go the end of the aisle, then you go this way. So the route is quite fixed. Of course, you have some freedom. Again, the freedom is the randomness in the environment. Yeah. So it happens. Yeah. You don't need to avoid it. It's the nature of the problem. Yeah. So when you test the different policy, when we test different policy, right, against different heuristic, we also simulate the randomness in the environment. This type of randomness. Yeah. Okay, so time for successful story 4.2. All right, so in this story, the problem is slightly different. The problem is in a factory. There we have a little bit more control about the environment, meaning much less randomness and uncertainties. So we have several machines. We have set of jobs. We need to schedule jobs on different machines before their deadline. Yeah, so it's the job shop scheduling problem. So in this type of problem, of course, okay, so I introduce the problem first. So some definition quickly. We have n jobs, n machines, and each job contains several operations, and these operations are ordered. Yeah, so you need to do this first, then that operation. So they are ordered. And each machine at each time can only process one operation. And also operations has a different processing time on different machines. Yeah, so these are problem characteristic. And the optimization objective of job shop scheduling is to find a schedule, a match between operations of a job and the machine such that the total make span is minimized. So the make span meaning the time when all jobs have been processed. Yeah, so this is a very clear optimization problem. And just in practice, so we work together with a company on this problem, so they give us problem instances. So is their jobs machine looks like. And of course, also we know this information of orders and the machines and the process time. There's still some randomness in the system, right? So it's unavoidable for all real-world optimization problem. Okay, so this problem, job short scheduling problem, has been studied in the OR research, OR community and optimization community for decades. Many years, right? So they propose a lot of different solutions based on mathematical optimization models, CP solutions, and the dispatching rule, heuristic rule, like I mentioned, the shortest processing time first, yeah? And also different type of heuristic, including evolutionary algorithms, different type of search algorithms. And also in the past 3-4 years, there are a lot of deep reinforcement learning approach appeared. For example, end-to-end. So end-to-end meaning I look at the current situation instances, I output the allocation, which is allocation from one operation to a machine directly, is end-to-end, yeah? But also a hybrid approach, meaning this optimization problem, I use a genetic algorithm to solve this problem to find the schedule, but reinforcement learning is used to control the genetic algorithm. Yeah, so not directly solve the optimization problem, but control the genetic algorithm. And the genetic algorithm is the one to solve the scheduling problem. So there are so many approaches appear in the past years, and the problem is they don't compare their solution against each other. It really bothers me. So they have one paper about the DRL approach, another paper about the hybrid approach in different way. They are different in some ways, right? But they don't compare with each other. So of course, so what we think is, okay, we first need to understand which one works better, right? So that's why we did this study with the master students together with the company. So we want to look at a different type of approach and want to look at how they perform on benchmark instances, but also real scheduling problem instances. And we want to look at not only performance, but also running time, because it's important in the real-world operations, scalability, like what I already said, whether the solution can be used to solve large problem instances, and the robustness and generalization. So this is I'm going to discuss in the next 20 minutes. All right, so I will pay special attention to two different DRL approach. One is end-to-end. I take it, we adapt it slightly from the paper from Zhang, 2022. Another one is we develop a hybrid approach. So we look at genetic algorithm and use reinforcement learning to control the genetic algorithm. So this is a hybrid approach I'm talking about. So first, the end-to-end. So this is how to look like end-to-end. So you have an agent. The action is really putting operation 23 to machine 3, right? You suggest the solution directly. So this is, and then the environment will give you a reward, the negative reward, and the agent will do next recommendation. So this is end-to-end. So I don't know whether I have time to go through this, but maybe quickly. The framework is quite nice. I think I would say it's quite nicely done. It's not from my work, so I can see that. And so it's from other authors' work. It's really nicely done. So what they do, they get the problem instances, and you see from the most left figure. So there you have a job information, you have a machine information, right? And then they use a heterogeneous graph to represent the problem instances. So they don't use a scheduling instance immediately. You use this graph to represent the information. And then they use a heterogeneous graph neural network to embed this information from this heterogeneous graph. And then at the end, they output the distribution of different actions. Then you can sample from this distribution to recommend the next action. Yeah, so it's how the whole framework works. Okay, again, to do DRL, you need to define the MDP, right? So here again, the actions are straightforward. They are just solution, so the allocation of operation to machine. And the reward is the penalty if expected the mix span increases. Yeah, so it is again aligned with the optimization objective. Okay, so again, the tricky part is how you give information to agent and how you encode this information. So in this way, I will go briefly. So they use this heterogeneous graph instead of the traditional machine scheduling disjunctive graph because this is less dense. And also in this way, you have a machine node, operation node, and you can also give the information of a machine. You can extract the information of machine nodes much efficient than the original graph. So and then you have this edge between machine node and operation node. It means whether you can allocate this operation to that machine. And arcs between operations, they are one direction, meaning this meaning precedence constraint between operations. Yeah. All right. Then, of course, again, you put different environment information on the nodes. Of operation nodes, you have information of number of neighboring machines, whether you are busy or not, actual or average processing time, etc. For machine node, you also put the relevant information there. And on the arcs, you put the processing time, sequential dependent setup time there. So, okay, after you have this representation of the problem instances, you need to make sure agents can extract this in the best way, right? So what they did is they use a graph attention network on the machine node. So in this way, then you can, hopefully the agent will know which operation is most important to schedule first. Yeah, so some operation maybe have an early deadline, right? So this, they use graph attention network to encode. Okay, so if you're interested, we can talk about this later, but I'm not going to discuss now. They use also PPO to, as an algorithm for the agent. So then, for this end-to-end, how it works, so the agent, see, okay, I have now need to schedule 23, operation 23, and I allocate it to machine 3. And because the expected make span at this stage is 9.5, but if I put 23 to machine 3, then the expected make span increases. That's why the agent will receive a penalty as a reward. Yeah, so this is how it works. Okay, so that is the end-to-end approach. Yes, so now I'm going to talk about the hybrid approach. And so this is, which means I'm going to use a genetic algorithm to solve the machine scheduling problem. So everybody knows genetic algorithm? Very good. I still want to show this figure anyway because Robert made it and it's cute. Okay, so basically we start with some solutions, and then through different generation, you improve a solution slowly, right? Increase step by step. And during this evolution, you do some, for example, crossover operation, etc., to change the solution, use a mutation to change the solution, hoping you get even better solution, right? So this is the idea of genetic algorithm. You do it many, many, many iterations, and eventually we hope the solution is much better than original solution. Okay, so of course, if you use genetic algorithm to solve a machine scheduling problem, you need to be able to represent the solution, right? So they use a chromosome. We use chromosome to do that. That is the representation. It has operation sequence and also machine allocation sequence. So basically, it's the scheme to map the solution found by the genetic algorithm to the actual allocation. Yeah, you don't need to know the details, but in this way, we can make sure that the representation of the solution is always feasible for the problem. Yeah. So it's the solution representation. And then if you use a genetic algorithm, you know that we also have a crossover operation, etc. We design the operations, crossover operation, but eventually this is the effect we want, right? If you start with the generation 0, the first generation, you have a make span 50, and you have a second generation, you can improve the solution quality to 46, and after generation 50, the make span is much smaller than the original solution. That's how genetic works. Now, after many generations, you will get the better and better solutions. All right, that is the genetic algorithm directly used to solve a job shop scheduling problem. Okay, so where is the reinforcement learning comes? So in the genetic algorithm, right, we need to make a lot of handcraft decisions, heuristics again. For example, with this production phase, we have a parameter for crossover, like crossover rate. Yeah? And for the mutation, same, we have parameters there. So usually we just try different parameter or use hyperparameter tuning to find the best one. But now we want to use deep reinforcement learning to learn dynamically during generation how to adapt these different hyperparameter such that it can help genetic algorithm to find a good solution faster. Yeah, so that is the basic idea. So then the interface will look like this. The environment here is not the job shop problem anymore. It's the set of solutions generated by genetic algorithm. Now, this is the environment that the agent is interacting with. And then, so what the agents, the state space of agent getting from this environment is the quality of individual solutions, like best value, lowest value, mean value, and how many generations still left, and how many generation that the solution is not improved. So this information is a state information. And the action will be decisions to tune genetic algorithm. For example, individual mutation rate, crossover rate, and other gene mutation rate. And the reward of the agent is the objective value increased in the new generation, right? You just look at the solution value. So it's clear. So basically, we are not using DRL to solve the job shop scheduling problem directly, but we guide the genetic algorithm in a smart way to solve it. And genetic algorithm is solving the job shop scheduling problem. Yeah. All right, so let's look at some experiments results then. So we did 3 sets of experiments. The first one, we look at vanilla job shop scheduling problem. Is the problem I introduced earlier. And the data set is one is benchmark data set. We have 3 benchmark data set from the literature. And the objective is make span. We want to minimize the make span. And during the second set of experiments, we have flexible job shop scheduling problem plus sequence setup time. We add more constraint in the second set of experiments. Yeah, so the schedule problem become more constrained. And in the third set of experiments, we look at the real data set from the company, and we add even more constraint to the problem. We add the release date, we add the night time, because some operations cannot be processed during night time. Nobody is in the factory, right? It's a very practical constraint, but everybody is ignore it in the literature, right? So we add this more constraint in the third set of experiments. So what we want to do, we want to look at 2 different types of DRL, how they perform against each other from different criteria: performance, running time, scalability, robustness, etc. Okay, so data sets. I'm not going to detail, but it's just the benchmark data set from the literature. It is there for like 30, 40 years. It's relatively small, but what I want to say. So they are just different. Yeah? So that they have different number of machines, different number of operations. And if you look at upper bound, lower bound, and the CP solution, you also see that some problems are more difficult because the CP cannot return good solutions. But anyway, there are a lot. Okay, so what we do, we train the 2 different DRL approaches. We train them on different sized instances. Yeah, we give a different sized instance to train these 2 different type of approaches. Okay, again, big table. I'm sorry, it's a really big table. But the first row is OPT, is optimal solution, right? We know the optimal solution for this benchmark data set. And then the second, the next 6 rules are heuristic rules. They are either you schedule the job with first deadline first or not. And so they're just heuristic rules, very simple. And the last one in the first box is the vanilla genetic algorithm. We use genetic algorithm to solve the problem directly without learning. And then here comes 2 different learning approach. DRLG meaning we have a DRL agent, end-to-end DRL, learn to how to schedule, but we sample, we use the best action to allocate. Yeah? DRLS meaning we sample the distribution of the actions, and we choose one. And the last one is our hybrid approach. So you do see that I highlight the best performing one with the red box. You do see that in some situation, end-to-end DRL give a better performance than hybrid approach. And in some data sets, that hybrid approach give a better performance. But if you look at vanilla genetic algorithm with the genetic algorithm with the help of DRL, you immediately see that DRL works, right? It really helps the genetic algorithm jump out of local optima. So you can have a much better performance. Okay, so yeah, it's a very complicated graph. But what we did, we trained 2 different approaches on fixed size, 15 times 10 instances. These instances we use to train these 2 different approaches. And we directly apply the policy to solve the different combination of the number of machines and the jobs. There are many different scenarios here. Basically, if the color is green, it means end-to-end DRL is better than hybrid approach. If it's reddish and yellowish, it means hybrid approach is better than end-to-end DRL. So you do see that there's no conclusion, right? So sometimes DRL works better, sometimes hybrid approach works better. So we plot this graph, so we show this here. X-axis is number of jobs per machine to show how busy it is, right? And you do see that the DRL is good at the genetic hybrid approach is good at either very simple case or very complex case. So you see the power of search there. But DRL is very consistent with middle difficulty instances. It has very consistent good performance. But for very difficult instance, you do need the power of search, a genetic algorithm, to get to better solution. So this is a conclusion from this set of experiments. I need to be a little bit quick. So distribution just means how consistent the output of different approach. And if you look at these 3 instances we picked, the OR2, they use a CP solver there, by the way. And for the first instance, it's easy instances. You can get optimal solution from OR2s. And also with hybrid approach, we also get a 0% optimality gap. Yeah? And the DRL, end-to-end DRL cannot match that performance. And also for the extremely difficult cases, this is the last one, also the hybrid approach is better than DRL. But for the OR2, we run it for 7 hours, still the gap is huge. So we don't know the performance. But at least hybrid is better than end-to-end DRL in this case. All right, so, okay. Main message here, yeah, you don't need to think, so also you don't also need to rate. Here, we add one more constraint, sequence dependent setup time. Yeah, because between jobs, you need a setup time, right? We add this constraint in the problem instances. And immediately you see that hybrid approach works much better than DRL. And we also look at the transferability, which means the bottom one. These are policy trained on the original flexible job short problem without this additional constraint. We trained that on this less constrained problem, applied directly on this more constrained problem, and the performance is better than the all other heuristics. Yeah, so the transferability power is also shows. If you look at the end-to-end DRL trained directly on the less constrained problem, applied to more constrained problem, the advantage is much less. So this is a real data. So the data from the company. So here the problem becomes really constrained. You have also release dates for different jobs. You have deadlines for different operations. You also have a nighttime constraint. Some jobs you cannot schedule during night. So for this, what I want to show here is what I want to show. Yeah, it's a good question. So this is the training and the validation results. So basically, it shows for the average make span, the hybrid approach is better than the DRL approach, right? But you do see the inference time, the hybrid approach, because it still uses meta-heuristic genetic algorithm in solving. That's why it takes still much longer than end-to-end DRL. You see that the power of end-to-end DRL is in really solving time is really quick. It's about 2 seconds, but the hybrid is 48 seconds. All right, so this is the performance table. It only just shows that DRL doesn't work anymore, end-to-end DRL. You need to use a hybrid approach for this highly constrained problem. So I will skip this one because there are too many tables. Then I really want to know when end-to-end DRL fails, right? So we know that for original flexible job short problem, sometimes end-to-end DRL is better than hybrid approach, right? But at some point, it loses its performance. So we add the constraint one by one in this case. Then we see actually, once you add the sequence dependent setup time, index 2, the end-to-end already worse than the greedy, I believe. Yeah, it is already worse than greedy algorithm. And if you add more constraints, the performance is just decreasing. You cannot be the greedy algorithm anymore. So basically, the still challenge of end-to-end in this highly constrained optimization problem is how you can get these constraints, right? Learn these constraints. I don't know the answer, but maybe you know. You are CP people. Okay, so but at least we got the answer we wanted to know, right? So given different type of approach, hybrid DRL, end-to-end DRL, or all other heuristic, when we should use what? Basically, we have a much more clear picture now. So for this type of problem, if we have full information and it's highly constrained, can we use DRL? End-to-end is still difficult, as you already see from the experiment results I show. But hybrid approach always work, right? So this hybrid local search or genetic algorithm, they are used a lot in practice in solving practical optimization problem. So if you add another layer of DRL to guide this meta-heuristic to make them go to the good solution much faster, why not, right? It's just the bonus. So hybrid approach works for the real complex combinatorial optimization problems. And they are highly transferable. The generalization capability is really good. Yeah. Okay, so coming soon is we will release this job shop scheduling benchmark. There we will give you, we will have a different simulation to simulate different instances. And we also implement the approach I just introduced and all set of other different heuristic. So we'll provide the environment for people to benchmark against each other's approach. So, well, my student promise it will be ready by the middle of August. Yeah, so if you are interested, keep an eye on it. And of course, I really feel the need to having benchmarks, right? I think you agree with me here. So we also organize competitions to provide benchmark problem instances and benchmark solutions to just let researchers help each other to see when we should use what solution methods, when this works and when this doesn't work. I think this is really needed. Okay, so I think I managed to go through all the slides in 90 minutes. These are references, and this is my team at the TUE. So thanks a lot. Questions?
Parameters, and then the algorithm runs. And here you're proposing to use reinforcement learning
Exactly.
Every iteration you decide the parameters and then
Yeah, yeah.
can you say a bit about the combination between the two? Like, have you looked at how often it chooses the same parameters, or how much this dynamism really contributes?
So we did look at the policy learned. So you do see that actually we expect when solutions are not improving a lot, then you see the DRL will recommend a higher mutation rate, for example. You do see that it gives different hyperparameter during search. Yeah. With the local search, we also do the DRL to guide the local search to select the operators. We do see that it's needed. You need to change the operators, and it does learn when you should change parameters. Yeah.
So in the lab session of Walter Kohl, the students, they were making under a supervised learning setting. So the lab session was about, okay, you do some runs, you generate data, and then you do supervised learning on that, and that will then be the learning-based policy that decides, for example, which nodes to do crossover on. So supervised learning versus reinforcement learning of these parameters.
Yeah. So. Okay, if you know what is the optimal operator to select at the current generation, why not using supervised? Because supervised is still easier than reinforcement learning, right? But the problem is we don't know. Yeah, that's why you need interaction using reinforcement learning to look a little bit further away, right? Further in the future. So I still believe reinforcement learning should be used for this dynamic tuning of hyperparameters or algorithm selection. Yeah. Oh, it all will also work. We also have that, yeah. Yeah, basically that's so this advantage of having learning to help this heuristic is just the bonus. You cannot do worse than that, than the original heuristic, yeah.
For the keeping problems in particular, PPO was kind of the agent of choice. Could you give maybe some reason why PPO was chosen, or did other agents just fail when that succeeded? Or
So why it failed?
just why PPO in particular?
It doesn't really matter. Yeah, so my experience is for you talk about this first problem, right? So a PPO or a DQM, they will all work. Yeah. Also, model-based planning will work. But I don't know whether model-based planning algorithm will work in real world because it heavily depends on the simulation, and so it's restricted to the simulator you built. But model free is a little bit, I hope, is more, how to say, robust against the way you build a simulation model. But we tested the model-based algorithm. It also gave a much better heuristic than the others. Yeah.
All right. Thank you very much for this.
Thanks.